entire issue that has to be dealt with to improve mathematics education, but it is the cornerstone. So standards determine the end-of-year goalposts for each grade. Standards, assuming that they're well written, guarantee coherence across the grade levels. So, for example, they guarantee that the same subject is not taught 3 years in a row, and that important topics are not missed. Standards determine the content and emphasis of tests, for better or for worse. I'll comment more about that later. Standards especially influence the selection of textbooks, which is the part of policy, education policy, that has the most direct contact with children in the classroom. And standards form the core of teacher education programs. So as was mentioned before, I'm one of the authors of a study called The State of State Math Standards, 2005, which examined each of the state's math standards in the country. There were co-authors to the report, Bastian Brahms, Thomas Parker, William Quirk, Wilfred Schmidt, and Steve Wilson, whose brother is actually in the audience. Now, let me get straight to the point. What's wrong with Washington standards? Our evaluation of it was an F. So let me just start with an overview. For one thing, there's excessive use of calculators, and calculators begin already in first grade. The standard algorithms of arithmetic are missing. Algorithm means a procedure, a systematic procedure. So the standard algorithms of arithmetic means that the standard procedures for adding, subtracting, multiplying, and dividing. Washington standards have a poor development of fractions and decimals, which I'll talk about in a minute or two. And the algebra standards are extremely weak. There's no mention of the quadratic formula. The treatment is limited fundamentally to linear equations. The word proof, as I recall, appears once in the standards in some platitude, but it should be attached to the standards of geometry, and it's not. The problem-solving standards are diffuse and weak, and there are too many standards that are completely unrelated to math. So let me give you an example of that, or several. Certainly interesting topic, but the question is, do they really belong in a math class? Problem solving. The focus of the Washington standards is really on talking about problems, a discussion of what it's like to solve problems, rather than actually focusing on solving problems. So you'll find in the standards, Washington standards, long lists of vague and generic tasks like gather and organize the necessary information or data from the problem, or use strategies to solve problems, generate questions that can be answered. Now these kinds of lists are both misleading and useless. They're misleading because that's not how you learn how to solve problems. And they're useless because they give no indication of the type of problems that are needed at each grade level. Let me give you an example. A first grade sample problem says, a classroom is presenting a play, and everyone has invited 2 guests. Enough chairs are needed to seat all the guests. There are some chairs in the classroom. Can I see a show of hands for the answer? Jim will administer a short 10-minute quiz, so it comes up. Another example at the opposite end of the standards, the grade 9-10 standards, asks, is it reasonable to believe that women will run as fast as men in the Olympics? The information provided consists of nothing more than a list of running times of men and women for an unspecified distance for several years of Olympic Games. Could lead to a long discussion, but the amount of math content is questionable. Calculators. Well, the standards are very clear on the emphasis of technology and calculators in particular. The standards say right at the beginning, technology should be available and used throughout the K through 12 mathematics curriculum. In the early years, students can use basic calculators to examine and create patterns of numbers. As I mentioned, calculators are introduced in the first grade. For example, a calculator standard in the second grade says solve problems involving addition and subtraction with 2 or 3 digit numbers using a calculator and explaining the procedures used. Well, let's deconstruct this standard, as they say in the English business. For one thing, second graders should be adding and subtracting 2-digit numbers by hand. It's a fundamental exercise in the understanding of place value, and students need to achieve a fluency in the use of the standard algorithms of arithmetic, including addition. Secondly, explaining the procedures used. Are we talking about making a list of the buttons that you press? Fractions, very important. Fractions are an essential prerequisite for learning algebra. So they're introduced for the first time in 4th grade. Standard says explain how fractions with denominators of 2, 3, 4, 6, and 8 represent information across the curriculum. For example, interpreting circle graphs or identifying the fraction of states that border an ocean. Now, the curiosity here is that there are 50 states, and so you would expect to see 50 appear in the denominator, at least initially. So there's some difficulties. 5th graders use calculators to multiply decimal numbers before they learn the meaning, that is to say the definition, even of fraction multiplication. Now, for this purpose, you need to understand that decimals are a type of fraction. It's just a notation for certain kinds of fractions for which the denominator is a power of 10. So what this means is that 5th graders are asked to use technology in a rote way without mathematical understanding. So it's just rote use of technology with button pressing. The explanation for what it means to multiply 2 fractions or divide comes a year later, in 6th grade. So in grade 6, we see the standard explain the meaning of multiplying and dividing non-negative fractions and using words or visual or physical models. For example, word size or equation. Now, size accomplished through repeated subtraction. And example of fraction division where you find the quotient of 2 fractions by repeatedly subtracting. However, that's not an adequate definition. It's actually, and this goes to the 2000 Nctm Standards, which gives a correct definition. So, to understand what I'm talking about, consider the fraction division of 1/3 divided by 1/2, and start repeatedly subtracting 1/2 from 1/3. You can't do it even once because 1/3 is smaller than 1/2. So repetition cannot explain what is meant by division of fractions. Correct definition must be given. Well, let me now turn to patterns. And the first step in understanding the role of patterns in the Washington Standards comes from the website of the Office of the Superintendent of Public Instruction. And there we find a definition of mathematics itself. The website defines mathematics as the language and science of patterns, and then there's a discussion there, a couple of paragraphs. And you see in the last paragraph, in the bold, stands for the first time that mathematics is an experimental science. It's the study of patterns and it's experimental science. Well, how do patterns appear in the Washington Standards? They appear all over the place, but I'm going to focus on 6th grade because we don't have all night. So this is the first of a couple pages of standards devoted to the study of patterns as an end in itself. Now there is a legitimate role for understanding patterns up to a point in the K through 12 curriculum. I mean, certainly we want children to understand the sequence of even or odd numbers, or a sequence of perfect squares, and then later on we want students to understand arithmetic or geometric sequences. However, the utility of the study of patterns is very limited in the K through 12 curriculum. But here we're asked to recognize or extend patterns and sequences using operations and alternate between terms. Create, explain, or extend number patterns involving two related sets of numbers and two operations and so forth. Use rules for generating patterns, e.g. the Fibonacci sequence, the bouncing ball, and technology, of course, makes the entrance. Now you have to ask yourself, why? What do we get out of studying patterns, using substantial class time on patterns, when at the 6th grade level, the fundamental issue is rational arithmetic, the arithmetic of rational numbers, an essential prerequisite to algebra. Well, they go on. They're somewhat redundant. Select or create a pattern that is equivalent to a given pattern. I don't know, maybe they clap their hands and write numbers that go with it. The last of these pattern standards for 6th grade is particularly intriguing. It says, identify patterns involving combinations of operations in the rule, including exponents. For example, 2, 5, 11, 23. Now the words sound fine, they're good English words. It sounds like a sentence. But if you think about what does it actually mean? Identify patterns. Does it mean give the formula for the nth term? Give the rule? The singular rule? Well, 31 for the next one and continue. But you could put anything else too. According to the guidelines of the question, you could start going backwards. You could say, well, I don't want to be any more than 29 years old. That's what my mother told me for years. She was 29 years old. So now we start going backwards. So 29, 26, 23, and 20 for the next row. Now, what is the point of arranging these numbers in a triangle? How does that contribute to the problem? Apparently, it's there to obfuscate the simple rule of adding 3 to a number, which is really the only thing being tested here. And so fundamentally, the way the question comes out is kind of a distorted IQ test question, which really has only a remote connection to math of adding 3. Well, let me now turn to a more general question. Why are most state standards, including Washington, so bad? Well, the National Council of Teachers of Mathematics, or NCTM, has had immense influence on state education departments and K through 12 mathematics education in general. Most state standards adhere very closely to the guidelines published by the NCTM. So there's a certain sameness to the state standards, which accounts for why the grades nationwide were so low. Now, 3 documents published by the NCTM have had particularly significant influence on the United States mathematics education, and of course, Washington's in particular. An Agenda for Action, which came out in 1980, really was the blueprint for the other documents. An Agenda for Action called for problem solving to be the focus of school mathematics. And it said that difficulty with paper and pencil computation should not interfere with the learning of problem-solving strategies. Well, how would this be accomplished? Well, it's simple. You give everybody a calculator. All students should have access to calculators throughout their school mathematics program. So whether they learn their multiplication tables or whether they're fluent in long division won't hinder them from solving real-world problems, or so the theory went. An agenda for action called for decreased emphasis on performing paper and pencil calculations with numbers of more than 2 digits. And interestingly, it also asked for a de-emphasis of calculus. It argued that calculus should no longer play a central role in mathematics education. Now this had profound effects starting in the early 1990s. Many of the so-called integrated math programs, and you probably encountered some of them, like Core Plus, IMP, there's one being held up here.
Crap Plus.
Which one?
Crap Plus.
Oh, yes.
Or minus.
They radically de-emphasized the prerequisites to calculus. Now, what are the prerequisites to calculus? Well, algebra, geometry, algebra 2, trigonometry. It isn't that these texts eliminated it altogether. It's still there, but they're sort of incidental discoveries on the way to solving real-world, quote-unquote, problems. They're not developed in a systematic, logical way that's demanded by the subjects themselves to achieve internal coherence. They're just sort of incidental on the way to solving some sort of problem. And, of course, the result is that they're not well learned. The next document, the 1989 Nctm Standards, is probably the most important in terms of the influence even today. The Nctm Standards said the new technology, I suppose it was TI, what was it in 1989, TI something or other, which is now considered ancient. But anyway, that technology not only has made calculations and graphing easier, it has changed the very nature of mathematics.
Ooh.
So all of us math professors were getting ready to mail back our PhDs. We just no longer mattered. And the Nctm Standards therefore recommended that appropriate calculators should be available to all students at all times.
At $100 a pop.
Yeah. Right? The 89 Standards called for more emphasis on collection and organization of data, which is one reason why you see so many statistics and data analysis standards in the K through 12 standards, even starting in many states as early as kindergarten. They're certainly heavily emphasized in Washington. The 1989 standards called for a de-emphasis for the grades K through 4 of long division, and even, I didn't put this one down, but even long division without remainder. I called for a de-emphasis of paper and pencil fraction computation, which really is the death knell for algebra, since fraction arithmetic is the fundamental prerequisite. An end to rote practice, which is the Nctm's way of saying practice. And similarly, rote memorization rules, memorizing. And teaching by telling, which is to say, teaching. The 1989 Nctm Standards also asked for less emphasis in grades 5 through 8 on manipulating symbols. Well, there goes algebra. They already killed it in the previous block, but in case there was anything left alive, they could catch it in grades 5 through 8. Memorizing rules and algorithms. Well, we've already talked about algorithms. Practicing tedious paper and pencil computations, and aren't they all tedious? And finding exact forms of answers, which is, let's get rid of math altogether. Well, the next document in line is the 2000 Nctm Standards. And because of the outrage and the jokes, the Nctm revised these standards in such a way as to make it less subject to ridicule by decreasing the extreme rhetoric. But nevertheless, it continued to promote the same damaging themes. An overemphasis of calculators, patterns, manipulatives. These are plastic devices which are intended to reveal mathematical ideas. And they continue to promote estimation over exact calculation and promote and over standard algorithms. And in general, over a coherent development of mathematics itself. Now, to be fair, the Nctm has done some good things recently. There's a new document out called the Nctm Focal Points, which
sort of acknowledges, well, you know, maybe kind of sort of you should have to do the multiplication tables and remember them and algorithms. Actually, not kind of sort of, it nails that down. It says you must learn your addition facts, your subtraction facts, your multiplication and division facts, and then understand how the standard algorithms of arithmetic work and become fluent in their use. So this is a step in the right direction, and Jim Milgram will tell us more about that and the potential benefits of this recent move, which he had a lot to do with, in a few minutes. Well, let me turn now to the all-important textbooks. This is where things really go bad with parents. This is when they go to their closets and pull out their pitchforks. You see on this list, and rightly so, a number of NSF-supported math programs for K through 12, and I imagine you'll recognize a few of them. Turk, Incorporated, Investigations in Number, Data, and Space. Core Plus is in there. IMP, Integrated Math Program, Connected Math, some of which you're probably very familiar with. So these are your tax dollars at work here. Now, what do mathematicians have to say about textbooks? Well, like any community, there are divisions and disagreements, but for the most part, mathematicians take a very dim view of what we might call anti-math books. The most public articulation of the community of mathematicians came in 1999, when more than 200 university mathematicians added their names to an open letter to then U.S. Secretary of Education Richard Riley, calling upon him to withdraw recommendations for Nctm line textbooks, including Connected Math or Plus. The list of signatories was significant. It included 7 Nobel laureates and winners of the Fields Medal, which is kind of like the Nobel Prize for math. It's the highest international award for mathematics. The signatories included math department chairs at many of the top universities in the United States. And it also included several state and national education leaders. So it wasn't just purely ivory tower. There were people who signed who had a great deal of classroom experience. It's significant for the future and very positive for the future that 7 of the signers of this letter now serve on the National Mathematics Panel, which we believe and hope will design good policies for the future. Well, how did the Nctm respond to this letter? I don't have it on this slide, but it's nevertheless true that within a week or two, the Nctm sent its own letter to Education Secretary Riley, explicitly endorsing the books that the mathematicians called upon the Education Department to withdraw. Well, that didn't do much. Parents, perhaps there are some in this room, may have used the letter to argue against these bad programs, these weak mathematics programs for their children. And it became useful enough so that in 2004, the Nctm president, Johnny Lott, at the time, posted a denunciation of the open letter on the Nctm website, and I think it's still there, entitled "Calling Out the Stalkers of Mathematics Education," including those mathematicians. So it says in part, "Consider people who use half-truths, fear, and innuendo to control public opinion about mathematics education. As an example, look at websites that continue to use a public letter written in 1999 to then Secretary of Education Richard Riley by a group of mathematicians and scientists defaming reform mathematics curricula developed by the National Science Foundation grants. A small group continues to use the letter in an attempt to thwart changes to mathematics curricula." Guilty. Yes, that was exactly our intention in writing the letter, to thwart the use of these substandard mathematics programs. Fine. These are certainly reasonable problems. But Wilfred Schmidt of the Harvard Mathematics Department, who was a co-author on the Fordham Report, says, "These are the most difficult addition and subtraction problems for the fractions that I could find in the Turk 5th grade curriculum, which is also described as suitable for 6th grade." Now, one of the problems with Turk is it relies very heavily on clock faces to do fraction arithmetic. So students move a hand around the clock face, a certain fraction, and then another distance, and they look what time it is, and then they add their fractions that way. It's not the only way that they do it in Turk. They also have Q's and air rods. But they don't really have exercise in finding a common denominator, which is a crucial skill for algebra. What happens when the numbers in these fraction equations turn into letters? Do they pull out their clocks and go with 8 minutes in the PM and B minutes in the AM, right? Basically, Turk puts students 2 years behind. And that's one reason why parents are very upset, and quite rightly so. Well, let me pull back and talk a little bit about the math wars, some of the issues, points of emphasis. The Nctm has been, at least until recently, the right-hand column. So their interest is on pedagogy. How do you teach? That's the primary emphasis. The critics, such as myself, put the major emphasis on mathematical content. In fact, that's pretty much all the emphasis. Now, what goes along with that? Well, it's skills-based. There's an emphasis on cohesion and clarity. There's a recognition that proof is the centerpiece of mathematics. On the other side, from the other point of view, we have the notion that you should learn skills as you need them for real-world problems. You don't need to practice and develop them to achieve fluency. You just find them when you need them. There's an emphasis on discovery learning and on different kinds of learning styles. Now, there's a lot of history to this conflict. It didn't just begin in our lifetimes. The right-hand column traces its origins back to the Romantic tradition, back to Jean-Jacques Rousseau and even earlier. But there was a famous book by that philosopher called Emile about a child who unfolded in a natural way in isolation from civilization. And just the idea is that if a child left to his own devices, you just water him and give him a little sunlight, will blossom into a mathematician, a scientist, an artist, you name it. They just grow like plants. The basic model for this point of view is maybe described as kindergarten, in contrast to the classical tradition. Back to Plato, which has as its model the university, disciplined instruction, focused, goal-oriented. The Romantic model of kindergarten, you see it historically for the last 100 years from time to time. It's heavily promoted by colleges of education, activity tables in classrooms. Maybe you want to do math on Tuesday, you go to that table. Maybe you want to finger paint the next day. The child knows best. The teacher should be a guide on the side, not the sage on the stage. That's what we pay them for. Well, who's on which side? Well, on the left side, we have parents, mathematicians, academics. On the right side, now, of course, there are exceptions. I mean, this is not an ironclad thing like all dichotomies. This one has exceptions. On the right-hand side, we have colleges of education, school administrators, and unfortunately, many corporate leaders. It's a sad fact that corporate foundations have funded some of the most destructive tendencies in mathematics education. I think many of them are starting to wake up to what has been going on. And Jim will talk about the economic consequences of this misdirection. Well, the root cause, aside from ideology, is really mathematical ignorance. Mathematical ignorance of district and state K-12 math leadership is the single greatest barrier to effective education. Most math curriculum experts are mathematically weak. They make bad decisions not only because they blindly follow the Nctm standards, but also because they don't understand mathematics very well themselves, generally at a level far below that of classroom teachers in the schools that they serve. Now, there are exceptions here. I've met some excellent math leaders, but this is a tendency. The mechanism leading to this paradoxical state of affairs is that the weakest math teachers are usually the first to embrace the latest education fads. And you might think back a few years to whole language learning as an example in another field. And these people are consequently rewarded by principals and other administrators for their willingness to be innovative. And this kind of innovation has a higher priority in the United States than proven effectiveness. And effectiveness is just unchanging if you find it, whereas innovation is exciting. The weakest teachers rise through the administrative ranks in this way, and the least competent teachers end up advising senior administrators and gain authority over mathematics programs at all levels. The result is bad standards, bad books, bad tests, and bad teacher training. Would anyone want to leave in charge of writing new state standards the same people who wrote Washington's current standards?
No.
It's possible you could go from F to a D, but that's not a great goal. Does anyone want to leave in charge of textbook selection? The people who chose TURP, CMP, IMP, and Core Plus. By way of analogy, should the surgeon who consistently amputates the wrong leg be in charge of the hospital? Mathematically competent people must be given actual decision-making power within state and district bureaucracies. I'm very pleased to observe that there are a few legislators here tonight, and you can talk to them. They'll talk when we're done. And I'm glad to see that they plan to work together to rise above politics and partisanship to look out for the best interests of children. So, recommendations. Well, number one, completely rewrite state standards or adopt already existing high-quality standards, such as California's, Indiana's, or Massachusetts. Those were the 3 states that got A's. Appoint university mathematicians, and that doesn't mean math education professors, it means mathematicians. Appoint experienced classroom teachers, not the ones who rise through the ranks that I described. Appoint classroom teachers from the classroom who get good results. Appoint them to high-level positions with decision-making power over standards, textbooks, pacing plans, state assessments, and in-services. And shift control of college teacher education courses away from colleges of education into subject matter departments. Let me end with one last comment about the textbooks. Where's the Math? The organization which sponsored tonight's event is a major resource in this state. This is an extremely valuable resource, and let me point out that the parents involved in this organization are highly educated, highly informed. There are dozens with PhDs, there are lawyers, there are business leaders, there are doctors, including professors of medicine. When they complain about these books, it's not because they're insisting that they don't want their children to learn higher order thinking. What they're trying to tell the leaders, including the legislators, is that there is something desperately wrong with those books that put us 2 years behind. And what the Where's the Math people will tell you is, don't jump out of the pot into the frying pan. Once we get rid of TURP, don't take something that's almost as bad like everyday math, which seems to be... So I think I've overstayed my welcome. Thank you for your attention, and I turn it over to Jim.
I think as Dr. Klein brought this up, let me take a moment just now to introduce the 3 legislators that at least I'm aware of that are in the audience, and perhaps you might stand. Representative Ross Hunter, 48th District of Medina. Representative Glenn Anderson, 5th District of Falls City. And Representative Fred Jarrett, 41st District of Mercer Island. And actually 2 of them are going to be on the program, and I know that all 3 of them will be more than happy to field questions later on. Our second speaker has been a mathematics professor at Stanford University since 1969. He and colleagues at both Stanford University and UC Berkeley were on the team that rewrote the current California mathematics standards and framework for the California State Board of Education in 1998. He is a member of the National Board for Education Science and the NASA Advisory Council. He became interested in K-12 math education primarily as a result of his experience at the University of New Mexico during a leave of absence from Stanford. It was then that our speaker came into contact with otherwise bright and hardworking students who were severely handicapped by weak K-12 math education programs. When he returned to Stanford, he found, to his surprise, that his students also appeared to have diminished skills in math compared to their counterparts of 15 to 20 years ago. We're very pleased to have with us tonight Dr. Jim Milgram to share his expertise with us.
I guess it does. Now, does this work? It certainly isn't where I wanted to start. Okay. So, this is from the Mercury News, which is the San Jose paper, I guess late last year. And I think that pretty accurately reflects the perspective, at least in Silicon Valley, on what's happening. So here's the way we kind of see it. As David said, I'll start by looking at what the consequences are. So, in fact, the economic survival of this country is in the balance here. And let's look at what's happening. Our major high-tech industries, including IBM, Intel, and TI, have moved or are already moving both their research and their manufacturing totally offshore. Those jobs, once they leave, and they're leaving now, don't come back. Major old-time industries such as GM and Ford are cutting large percentages of their workforces in North America and closing manufacturing plants. And I mean large, 30 and 35%, and a third of their plants. We cannot produce sufficient engineers and other high-tech workers. NASA and the national labs are not able to replace their aging top scientists and engineers, to say nothing of the problems that high-tech industry is having. In fact, people at NASA Council, NASA Board, and I'm not who was ever appointed to that board, serving with so, you know, other pulled me up and asked me onto the board. I asked them whatever prompted them to ask me. And I hope the answer was my outstanding work in robotics. But it wasn't. What they said was what I wrote up there. That NASA, the scientists and the engineers that did the Apollo program, that did the shuttle program, are now aging and retiring, and they are not able to replace them because, you see, NASA, being a government agency, has to hire U.S. citizens. And these are the measure of the problem that we're facing, in all seriousness. The root cause of this is a failure in the mathematics education in K-12, and particularly we can track it back to K-8, and even more particularly, the failures are already evident in K-4. And ultimately, we cannot avoid the fact that these failures are tied to the way we train our teachers, our pre-service teachers, in mathematics. So what's the result? Well, This is a problem from the WASL, what is it, WASL? Yeah. The WASL practice exit exam, the 10th grade exam. It was striking, and this is the worst. For Fordham Foundation and for Smith Richardson and for Achieve, a group of us, me, Dick Askey, and a few others, evaluated state assessments a couple years ago. And what we found in most state assessments was an error rate of 20%. So 20% of the problems on state assessments in 4th grade, 8th grade, and 10th grade were mathematically incorrect. Well, the WASL puts that number to shame. In fact, 5 of the first 8 problems on the practice exam are mathematically wrong. And here's one of them. What's wrong with this problem? Well, what's the answer to this problem? To be honest, I haven't got a clue. I mean, I think what they had in mind was 7 plus n squared. But why not just put, because I don't particularly want to work very hard, why not put 43 as the answer? And then you could go further and you could say 23 is the next, 11 is the next, 7 is the next. Then you can go back up, 11, 23. But maybe that's too hard. Let's just repeat. So let's do 7, 11, 23, 43, 71. I mean, why should those be excluded? What earthly reason do you have to choose one over the other? This isn't mathematics. What this is how should I say it? It's trained responses. So what you get are students that don't know the code can't answer the problem. And the students that know the code get the answer right, whatever the heck that answer is. So this is what we're seeing. This isn't mathematics, and literally, I don't know what it is. Okay, now on a more serious issue, I mean, not that one shouldn't take in Washington's test seriously, but this is the national test, the NAEP, the National Report. And in October, I and 2 other mathematicians were asked to evaluate the algebra questions on the NAEP. So Brookings Institute asked us to evaluate these. And here's the result. Of the 41 8th grade NAEP problems provided, 8 were incorrect and 1 was meaningless. 8. That's 20%, right? Close enough. And that's about right. That's the error rate that we were consistently seeing in the state tests. So at least we're consistent here. But it was a little worse than that, because you want to see some mathematics, and 10 of the problems were just about vocabulary. Vocabulary, by that I mean something like this. You look at a question, identify the square in the following list of figures. So when I say vocabulary, that's the kind of question I mean. So here we are with our algebra. We've got 8 which were outright wrong, 10 more which were vocabulary, and that left, what, 23? Yep. Questions that were acceptable, but actually they were very low level. Now in grade 4, we also looked at them. We had 22 grade 4 questions, and 4 were incorrect. What's the percentage? About 20. It's consistent. And 4 others were essentially vocabulary. That's consistent. And only 1 was judged mildly challenging at 4th grade level. And the 3 mathematicians involved all agreed with this assessment. Here's one of them. This is even worse than the previous pattern. My comment, so this is from the actual material that I sent back to Brookings, but, and so the comment in red is mine. Everything I can think of is wrong with this problem. It is not well posed, and I cannot imagine what mathematical abilities it might be testing. So this is the state of these things. And this is maybe a way of explaining why mathematicians don't trust patterns. All right, so that's what we're dealing with. We're dealing with a monumental ignorance of the subject, and the problem is, how do we fix it? Well, there has been some good news in spite of the gloomy discussion that David just finished. That over the past 3 years, the two basic communities, the math education and the mathematics community, that is mathematicians, math educators, and teachers, have begun to cooperate at the national level to bring the strength of the international curricula to the United States. When we really closely compared what we were each saying, what it turned out that a lot of the problem was that we were using the same words to mean different things. And when we actually compared what we were saying rather than the words we were using, it turned out that we had a lot more in common than we thought we had. But this was a really huge effort to get through that language barrier. So here's what we come up with. There are 3 dimensions to the problem. The first is standards, which David has discussed. The second is curricula, which David has discussed. And the third is teacher training. But I'm going to discuss them all anyway. Okay, our state standards can be characterized as an inch deep and a mile wide. And that's not just Washington, that's state standards in this country. It's not unusual to have 100 or more standards in any single grade, which leaves you precisely 1 lesson to cover each standard, if that. Well, the California standards exist, and they come in 2 flavors. First, there are the general standards. Well, they're better than most. They're maybe only a block wide rather than a mile. Well, some people say a half mile. But at any rate, there are too many of them. And then there's another group of the standards, which are called the green dot standards by those of us in California. And the reason they're called the green dot standards is because they have green dots on them. So here is the first page in grade 1, and you see the green dot standards, which are most of the green dot standards actually in grade 1. And if you look at those standards, count, read, and write whole numbers to 100, compare and order whole numbers to 100 using symbols for less than or equal to or greater than. And then you look at, say, the next standard, you see why that's not a green dot standard. Represent equivalent forms of the same number through the use of physical models, etc., etc. Who cares? The green dot standards are the key standards. They're the things that the kids need to know at that level. That will, if focused on by instruction of more than 1 lecture per standard, will result in the kids learning the mathematics they need to know in order to learn the next level of math they need to know. Math is hierarchical, and we cannot forget that. So, when instruction dots in isolation, what they do is they focus on basic throughout the grades through 6. And here they are. Those are the 6 basic topics that the green dot standards work on. Place value and basic number skills, fractions and decimals, ratios, rates, percents, and proportions. What core processes, that's the basic processes of algebra. The things you do to solve equations and the things you do to solve inequalities. The next thing is functions and equations, and finally measurement and basic geometry. These are the 6 topics that kids have to learn by the time they get through 7th grade. Well, 7th grade here, 5th or 6th grade in high achieving countries. And now a very recent development has happened that actually changed the landscape that was just alluded to by David. On September 12th, the Nctm released the curriculum focal points, and the curriculum focal points are a brand new departure for Nctm that they list as a clarification of the way the Nctm standards should look when a curriculum is developed from them. Now, they include the advice that there should be only 3 standards per grade, 3 topics per grade that should be worked on, and those should be worked on at least 60 to and preferably 80% of instruction time should be devoted to these topics. Well, these topics now. Here, just comments here. I think the only thing